Hi, today we're going to be looking at oxidation numbers, as the title slide says. So let me switch my pen and we'll get started. As a quick reminder, a quick do now to get your brain back into it, I want you to take a look at these reactions, identify which reactant is oxidized and reduced. I'm going to show them with just an O and an R. Feel free to hit the pause button. I'll count, give you a little time to think otherwise. By our first definition, combination with oxygen is oxidation. So the magnesium would get oxidized, oxygen being reduced. Again, looking at the second reaction, we're combining with oxygen, right? The oxygen is moving from the iron to the aluminum. So the aluminum would be oxidized, the iron would be reduced. It looks like in this third reaction that electrons are being transferred. The copper is going from a positive ion to a neutral atom, and the lead is losing and the copper is gaining. And looking at the last reaction, it seems similar, where there's going to be charges made where there are no charges to begin with. So the sodium is going to lose electrons and the chlorine gains. We do see some patterns here. It does seem to be that nonmetals are typically reduced, although it does also seem to be the case that in the second and third reactions that it looks like, metals can be reduced as well, which kind of leads into today's demonstration. I would love to do this reaction for you in person. I'll talk about this at the end, but maybe I'm going to try and do this one at home. We'll see what we can figure out. It's just really, it creates, I'll just play the video. I'll talk about it later. Watch it, take any relevant notes. I'll be doing the same.
For this experiment, you need some glucose, sodium hydroxide, potassium permanganate, and some water. Dissolve enough potassium permanganate in 50 ml of distilled water. Dissolve 2 grams of sodium hydroxide and 4 grams of glucose in 50 ml of distilled water and add it to the potassium permanganate.
Oh, they're going to lock the colors for me. That's very nice. Well, yes, I can. Yes, hopefully I can. Interesting. They got five colors. I thought I get 4. Although I have a hard time seeing either the yellow or the orange. Depends on the year. The one thing I will say is that I'll add to this is that this reaction was time lapsed. So this is a slow process, and I think this is something we can gather from most of these redox reactions. So the colors you saw correspond to different manganese compounds. Oh, I forgot the potassium permanganate. I probably should provide the chemical equation for that. Permanganate, found on table E of the reference tables, is a -1 charge. Potassium has a +1. It's a +1 -1 salt, so it's a 1-to-1 ratio. It does dissolve in water because it's a group 1 element, so this is a potassium permanganate solution. I'm actually curious, can I? Nope, I cannot draw on videos. Anyway. The colors you saw do correspond to different manganese compounds, so if we're going to tie this into redox, obviously we're seeing a color change, and that color change is indicating chemistry is going on, but what chemistry is going on? I mean, is the manganese getting oxidized or reduced? Looking at the charges, we're going from -1 to -2, that's going down by 1. -2, -3, that's going down by 1. -3 to +3, if we're just looking at the charge, we're going up by 6. So that doesn't really make any sense. As far as I can tell in the video, they were mixed and they were left to sit. And every time I've seen something happen in chemistry, it's almost never the case that the reaction changes gears like that. Suddenly where you'll get this reduction, and then this massive oxidation, big change in charge. So I don't think we have enough ability to take a look at what's going on here until we have a discussion about how we quantify oxidation. That might help a little bit. So I want you to try and take a minute for this top set of all the irons. Which iron is most oxidized? Which iron is least oxidized? I think you have the ability to like reason that out for yourself, and then we'll talk about the bottom one together. Great. So in iron, the element, it's neither, right? As far as I can tell. It's neutral, right? This is a neutral atom. It's in the element form. In iron 2 chloride, if you unswap, you get Fe2+. In iron 3 chloride, you get Fe3+. So I'm pretty sure that between the iron in iron and the iron 2 ion, that this is more oxidized. If we say, I believe we were going to go with, I'm going to write them this way. Yeah. Because now I can write this way. If we say that oxidation is losing, reduction is gaining, we're talking about electrons. The iron 2 ion has lost electrons relative to that iron atom. So we'll say it's more oxidized than the iron atom. The iron 3 ion, of course, lost another electron, so we'd say this is most oxidized. I guess you could say also that the iron atom is most reduced, if that makes sense. Right? So it's kind of like oxidized and reduced can be viewed as like a continuum, where the most oxidized is the least electrons and the most reduced is the most electrons. That should make sense. That being said, just like we saw with the previous lesson, things get weird once we talk about covalent compounds. So really quickly, I'm going to draw the Lewis dot structures. I'm going to bend one of the rules we have of Lewis dot structures, but I'm just going to show, yeah, that'll be a good enough structure. We're not going to break our octet rule. And then I'll show for this one I am going to bend our octet rule. But these are our Lewis dot structures for these 3 compounds. They all contain sulfur. Now, here's the thing. It's a little bit harder to have this discussion of oxidation is losing and reduction is gaining when all of your sulfurs are covalently bonded. For those who are wondering, this is the most oxidized, and this one is actually the least oxidized. If you don't know why, that's totally okay. Hopefully by the end of this, you will. But the way I knew that is by using something called oxidation numbers. And it's just a positive or negative number given to an atom in a compound or out of a compound, but to a specific atom to tell you how oxidized and how reduced something is in a compound. So going back, actually, here, this number here of +2, we can say like that number actually tells me how oxidized. And if the iron 3 ion is more oxidized, then maybe this number 2 and 3 will be pretty useful in describing the level of oxidation it has had. So that's obviously what I just said, so I'll just write this down to make sure the slide matches. This number, I wrote it and then I went back and then before it, it's fine. Number indicates level of oxidation. More positive is more oxidized. And then we're going to also say more negative, or I guess less positive, is more reduced. So the iron 2 ion is the more reduced of the two. It is possible to have a negative number or to have 0 as your oxidation number. The oxidation number is also called an oxidation state, which we're going to see on the next slide. But to determine your oxidation numbers, which is going to be the most important part of this process, we need to come up with some ground rules. But I'm going to try and build the ground rules in a way that makes the most sense. I'm trying to not overload you. Lemon tea. Excellent choice. So when determining the oxidation number, one of the biggest rule we're going to put down, which should show up later when we talk about the actual list of rules, is that we're going to treat a polar bond and an ionic bond the same way. That is to say, a calcium atom in a bulk calcium solid, well, the Lewis dot structure would look like this. That substance would be neither oxidized nor reduced, so we're going to call that 0. It's not oxidized, it's not reduced. If the number indicates that, well, it's not. In calcium chloride, if we're going to draw the Lewis dot structure, it looks like this. Now this atom has lost 2 electrons, so we're going to call that a +2 oxidation. Great, that should make a little bit of sense because this is just ionic bonding. Now, once we get into covalent bonding, it's a little bit more difficult. This structure here is diamond. So I'm going to draw a really zoomed in Lewis dot structure. So the idea is that each carbon is bonded to 4 carbons, is bonded to 4 carbons, is bonded to 4 carbons. And it just keeps going on and on. And they reconnect and they make this tetrahedral structure. But I'm saying the rest of the molecule continues on from here. I'm not going to worry about that. In a carbon dioxide, I'm going to draw this really quickly. In carbon monoxide, it actually looks like this. And then in methane, it looks like this. So what I'm saying is if you have a polar bond, I want you to treat the polar bond like it's ionic. It isn't ionic. But for the purposes of counting how oxidized something is, we said that getting in from a nonpolar bond into a polar bond can be viewed as redox, so let's treat it that way. Looking at CHs, the carbon has a higher electronegativity, so instead of having all these bonds, instead we're just going to treat it like carbon has all 8 electrons just for our counting. This means that carbon should have 4 valence electrons as an atom. This has 8. So that would be carbon in a -4, as it's like picked up more electrons. In this case, we're going to cross these out and we're going to give them all to oxygen. Now it looks like this carbon is very, very oxidized because it should have 4 now it has 2. Does that make sense? Did I do that wrong? I think I did that wrong. I'll come back to that. No, I think the two works. Never mind. Here, both of these oxygens would get these electrons. Oh my God! Bad structure. Bad structure. -2 points. Go to SGI. So this carbon would have no electrons associated with it, and then these carbons, because they're actually shared equally, those we will divvy up equally, and what we'd end up seeing is. Each carbon ends up with 1 electron. Oh my God, too many dots. You know what? I'm going to use an eraser. That would be so much smarter. Okay, a little bit cleaner, a little bit easier to say. Each carbon ends up with 4 electrons if we just snip them, and then this carbon ends up neutral. So we're going to develop these numbers, but what I would say is that in this continuum, this one is the most oxidized, and this one is the least oxidized. Or the carbon in methane is most reduced, and the carbon in carbon dioxide is the least reduced. Or you could say the carbon in methane is most reduced and the carbon in carbon dioxide is most oxidized. That's usually how I think about it. So just to come up with a couple of Quick ground rules, I've got a couple of examples in each case. Any element, whether it's diatomic or not, by definition, we're going to say has an oxidation number or an oxidation state of 0. And I like the word state because it kind of says like where you are now versus where you might be later, and that we're using a number to refer to that, but I like how it gets the point across. In any ionic compound, we're going to say that the oxidation number is equal to the ionic charge. So a sodium ion has a +1 charge, a chloride ion has a -1 charge. The oxidation number is +1, and -1. This is probably a decent time to make the distinction that I've just kind of been making the whole presentation, and I haven't been talking about it. Usually in class, I've referred to charges by putting number then charge, and now I'm suddenly talking about putting charge then number. This is where we draw the distinction. Technically, and no one's going to mark you off for this, but technically, charges, ionic charges, are shown number charge, where oxidation numbers are shown charge number. It's like a tiny little, very specific thing, but I'm just mentioning it. Calcium bromide I want to talk about a little bit more. The ionic charges are +2 and -1. But, okay, so like we're going to write that. The oxidation number for calcium is +2, and the oxidation number for bromine is a -1. For any compound, the sum of all oxidation numbers is 0. Well, that should make sense, right? +1 -1, that equals 0. +1 -1 is 0. For calcium bromide, though, something a little bit different happens. Wait, if it's a +2 and a -1, how is that equal to 0? When we assign oxidation numbers, they are assigned individual, like the number that we give is for each individual atom. There are 2 bromides in this compound for every 1 calcium. So what I like to do is I like to put the oxidation number on top, and then if I need to do some math to make sure that everything works out, I'll multiply this number by the subscript, then checking my math. So I would put like the totals on the bottom, and I put the oxidation numbers on the top. It's something I do. It helps me keep the 2 separate, but you should not be saying that a bromine has an oxidation state of -2. It's not true. Can't happen. Doesn't happen. So just that math step has to be present. If you have a covalent compound, we're going to assign temporarily all the electrons to the most electronegative atom in any given bond. So we'll start with HCl because it's easier. The HCl, I drew too many dots. Erase. Boop. We're going to assign all of these electrons to the chloride temporarily, and that means that this chlorine, not chloride, with 7 valence electrons currently showing 8 has a -1 oxidation number. The hydrogen has 1 valence electron, it's showing 0, that's a +1. Has none, should have 1. For water, same thing. If we assign both the electrons to the oxygen, the more electronegative one of the 2, what we get is that each hydrogen is a +1, the oxygen is a -2, so that still adds up to 0. And then for ammonia, the hydrogen ends up being the +1. Oh my god, too many lines. And the nitrogen actually ends up being a -3. Typically, we will put the positive oxidation number first in a compound. That's the same as listing them in electronegativity order, actually, based on this. Ammonia is the exception because we figured out the formula and we called it NH3 before we knew what it was. And then we said, oh wait, we're going to have a standard of naming things, and then, oops, we're not going to change it because ammonia is so common. If you're looking at a polyatomic ion by itself, the sum of the oxidation numbers, instead of being 0, has to add up to the overall ionic charge. So SiO3, it's a silicate anion. I'm going to draw it. It should look fairly similar to carbonate. Again, it's covalently bonded in the middle, so we can assign all of our electrons there to the middle, or to the more electronegative one. And what we end up seeing is that each oxygen is a -2. And it looks like the silicon should have 4. It has 0. It's a +4. But then again, if we do that math, +4 minus 6 equals -2. The ionic charge matches up with the she'll stop eventually. The ionic charge equals the sum of the oxidation numbers. That only works when you do multiply. All right, hang on 1 second. It's gonna make my video longer, but it's okay. Maya. Come here. Come here. Come on. Come on. Come on. Relax. I know. Hi. Shh. Sit. It's okay. Uh-huh. I know. Oh, no, don't walk on that. You want to get down? Go on. No, go on, get down. Just relax. Anyway, for ammonia, it works exactly the same way. It looks very similar to ammonia. Did I say ammonia or ammonium? I don't remember. But if we were to split each of these, each of the hydrogens would be a +1. The ammonia, the nitrogen would end up being a -3. And then if we add -3 plus 4 equals +1. And these rules actually do end up stacking. If you have a compound that is iron silicate, iron 3 silicate, I imagine the first thing we do is unswap the coefficients to get our ions. SiO2, SiO3, 2 minus. And then we would then look at this to figure out -2 plus 4. That's, of course, a +3. So like we can actually stack these rules on top of each other to say, oh, if it's an ion, you give it the ionic charge. If it's not an ion, or if it's a polyatomic ion or a covalent compound, you have to do more work. Those are all the rules. But we can boil it down to a couple of quicker things, like a couple of simple things to make our lives a little bit easier. In general, when hydrogen is in a compound, the hydrogen is going to be covalently bonded, and hydrogen has the lowest electronegativity of any nonmetal, I'm pretty sure, which means hydrogen is usually a +1 since it's got a low electronegativity. Is it always that? Well, we'll get to that in a second. Oxygen has a really high electronegativity, so it's almost always going to pull those electrons in. And then the only element that has a higher electronegativity is fluorine, which would have a -1 because it only makes one bond because it has 7 valence electrons. Wow. I spell so well. Group 1 elements, when found in a compound, right? Sodium as an element is 0. But group 1 elements will be a +1. Group 2 elements will be a +2. And then if you consider all of these and say compounds add to 0, well, then you can just kind of do math. Given your compounds, you can kind of like work backwards. Take those, put them together with the fact that like ionic compounds have their charges as their oxidation numbers, and you're good. That being said, they almost always have exceptions. Maya, come here. You want to go downstairs and bark at people? Okay. Go on. So you have to do math. Like I said, so if you get something where it's NaClO3, sodium ions are a +1, oxygens are usually -2. You end up doing math, and chlorine is a +5 in that compound. Or you'll see exceptions where there's something like, I don't know, hypothetical compound OF2, where, so in an oxygen-fluorine bond, fluorine wins, and so this oxygen actually has an oxidation state of +2. This, rare. Super rare. So rare, I'm done talking about it. It's not going to happen. You're not going to see it. So as some practice to give you something better to look at than OF2, here are 3 examples. Carbon in 3 different compounds, and I want to see if you can figure out the oxidation number only of carbon. We don't need to worry about the others. There's a reason, because they're all hydrogen and oxygen. I'm trying to make this a little bit more straightforward. So hit the pause button, do some quick arithmetic, figure out the oxidation number of carbon in each one. No, go ahead, try it. I trust you. Okay. All hydrogens are +1, all oxygens are -2. This has to add up to 0, carbon has to be a +2, this has to add up to 0, carbon has to be a +4, this has to add up to 0, so I'll write it bigger so I can actually do my math, because if you want, you can set up actual algebra, I know. So this multiplies be a +2, this is 2x because there are 2 of them, that's -8. Equals 0. We end up, that's actually +2 because I can do math. 2x would equal 6, x equals 3, and so your carbon's a +3. Now this is where I'm going to mention your reference table, because yeah, those numbers on the reference table that we've been using for ionic charge, they're not ionic charge. If you look, it says -4. Not 4-. And if you look at the top of your periodic table, it says suggested oxidation states or common it says something about oxidation states, which, hey, we're doing that today. But it's not all of them, because you can see that it lists -4, +2, and +4, and that's an example of it not being that. And I don't really want to go into why that's the case. All I want to say is just do math. If you get something that's not on your periodic table, just check your math. If you did your math right, then that's what it is. And if it's not on the list, so be it. I would almost prefer that that list not be there, because a lot of times I feel like students seem to think those are the only possible ones. The other part of this is to take the step and say, well, then what is a redox reaction? How do we know a redox reaction happened? And the way you do that, one way to do that, is to go through and assign oxidation numbers to everything and see if anything changed. So the first example is from the do now. I'm going to step in really quickly and figure out the oxidation number for everything. You kind of get used to it over time, and it just kind of rolls off the tongue or the pencil, as the case may be. All elements are 0, all oxygens are -2. Then you do the math and you get that the iron here is a +3 and the aluminum there is a +3. So we can kind of see that the iron went from a +3 to a 0 and the aluminum went from 0 to +3. And that should be consistent with the fact that we said that the aluminum got oxidized and the iron got reduced because it went. So a decrease in oxidation number is reduction. +3 to 0, 0 to +3. Looking at this one, we've got a +1 and a -1. Oxygen's a -2. Unswapped, the mercury's a +2. You end up figuring out that the nitrogen's a +5. That nitrogen's a +5 -2 +1 +2 -1. And if you look and you did your calculations right, nothing changed. So this is an example of a reaction that is not considered redox. And then here, this one was mentioned. One of my students mentioned it the day before recording this, talking about a neutralization reaction, if that counted as redox. And let's take a step in and figure out. This is a +1 because it's H+. This is OH-. So the typical charges of oxygen and hydrogen work out. -2 + 1 is a -1. And then we already talked about water. Nothing changed. Both of the hydrogens are a -1, and then they're both a +1, sorry, and they're both +1 over here, and all the oxygens, this is not redox either. So looking at the type of reaction, it looks like this reaction is redox, and this one is not, and this one's not. Neutralization, not a redox reaction. Double replacement, not a redox reaction. Single replacement is a redox reaction, and I'll save you some trouble. Synthesis, also a redox reaction, and so is combustion. The simplest way I can quickly pick out whether or not a reaction is redox is I look for an element that is an element on one side of your arrow and is in a compound in the other. I look for a symbol that's in an element in one case and in a compound in the other. So that happens in synthesis because two elements become a compound. In combustion, you have a hydrocarbon reacting with the element oxygen to make carbon dioxide and water. So there's your element. There are your elements. And in single replacement, I just circled the elements up top. Double replacement and I guess decomposition would also constitute a redox reaction sometimes. There are some examples that don't, which is why I didn't list it there. But that's why I say just look for compound, or look for an element and a compound. So to sum things up, there's your definition for oxidation number. There are several rules, but just think about electrons. I mean, there's things like you worry about ionic charge. The sum for a compound is 0, and oxygen is a -2, and hydrogen is a +1, and that pretty much gets you 90% of the way there. So I kind of want to give you guys the chance to figure out the oxidation numbers of everything here. As a summary, I'm going to tell you this in earnest. I'll say hit the pause button and figure it out. If you don't know how to do these, rewind back in the video because I've shown examples of a lot of these in previous slides in this presentation. But I'm going to get started. The first thing I'm going to do is I'm just going to go through everything on the page. I'm going to assign all the oxygens and all the hydrogens to what I know they have to be. The second thing I'm going to do is now I'm going to look for, are there things I can figure out? Well, there's 2 things here and there's 2 things here. But here, the sum is -2. This is going to be -6, so this has to be a +4. The sum is a -2. This is a -6. There are 2 of these. So this has to be a +4, but each one is a +2. Here, the sodium has to be a +1, and if we do our math, this is a +6. This will end up being a -2 because this is actually an ionic compound because this is ammonium, and that ends up being a -3. Thanks for watching. Oh, no, you want me to talk about the demo, what happens with the permanganate, right? So if you go through the permanganate, I can totally talk about this. I forgot. That's fine. I'll draw it at the end. So if we actually step in a little bit, what we see is that your charge is actually working its way down from +7 to +3. And I think that yellowy, orangey color is either +4 or +3, both. I'm not quite sure. That's why they were mentioning orange to yellow. But this, if you go in and actually look at the oxidation number, there's reduction taking place. And you might not have seen it by looking at the polyatomic, but now it's there if you actually look at the oxidation number of just the manganese, which is a really powerful tool. So when you go looking into glucose, you have to do a little bit of the math. It said sucrose in the video, but we're going to use glucose because the math is a little bit easier. Each oxygen's a -2, each hydrogen's a +1. That's +12 minus 12 equals 0. That means that the carbons actually are on average neutral. They're not all neutral. Some of them are positive, some are negative, but it adds up to neutral. And so what ends up happening is through reaction, these oxygens or these carbons will be oxidized and you'll get a whole host of compounds that'll pop out. And compounds like this and compounds like this, where the oxidation numbers for carbon have now changed. And that's what's going to really drive this process. So you need the base there to help the reaction happen, which I don't know if we'll even get to in the next 2 lessons. But the sugar is a source of oxidation. It gets oxidized. It's a reducing agent. It gets oxidized in the reaction. So you're actually breaking down sugar using the permanganate. When you do so in your body with respiration, it works differently. But the color here is indicating that this reduction is taking place. You can use any hydrocarbon, any like carbohydrate as a source for that. And that's why I have my brain going, because I have a little bit of potassium permanganate, and of course I have sugar. I don't have any sodium hydroxide, and I don't know if I have anything that'll fit the bill, I have some ash from a fireplace that if I filter it, I might be able to pull base out of it. So if I can make that work, I'll upload a video of doing this at home. I'll even tell you all how to do it. The hard part's the permanganate. Everything else you can probably find at home. But enough about that. I think I've explained where the demo came from, so you can see where that color change comes from. The last thing I'll mention is the further you get from 0 as an oxidation number, the more reactive the species. So while that purple permanganate ion is very pretty, it's also quite poisonous because this reduction happens fairly readily. Working your way back to 0 is higher stability. And that's kind of how this whole demonstration happens. So actually this time, thanks for watching.